Hello, everybody. Welcome now to this last session. So we are going to have two talks in this session. And the first talk is by Filip Moortgat. And I personally have known Filip for a very, very long time. And I just wanted to be sure that I introduce him properly. He did his PhD in Belgium at the University of Antwerp. Then he was a CERN fellow. And after that, he was at ETH Zurich for a while. And then he came back to CERN now. He's a CERN staff. And most importantly, he is actually the director of LHC physics program. And in that sense, he is really playing a very important role. And therefore, the ideal person to tell us about the experimental outlook. So here is, I give you Filip Moortgat.
Okay, now let me start with a little recap. So where is SUSY? Some people thought that we would find it very quickly at the LHC as soon as we turn on. I remember those days. There are plenty of good arguments for this as well. That did not happen. Other people thought we would quickly exclude SUSY at the LHC because after all, at the end of lab, we ended up with a Higgs exclusion up to 114.4 GeV. And SUSY requires a Higgs lighter than 135 GeV about. So this really was only for MSSM Higgs, light MSSM Higgs. There was only about a 20 GeV windows left. So this would be easy to exclude. However, nature put the Higgs exactly in the middle of that 20 GeV window. So we have this interesting puzzle. We cannot find it and we cannot exclude it. So there's now only one way forward, and that's keep searching for it. Now, any hint of where it could be? Well, we know natural's arguments tell us it shouldn't be too heavy. But the one new ingredient that the LHC has brought into the game, which is the Higgs boson mass, 125 GeV, tells us it shouldn't be too light either. So here I briefly remind you of this argument. I think it's probably been discussed by Pietro in more detail previously. So if you look at the Higgs mass in the MSSM, to bring it up from the Z mass to 125 GeV, you need corrections, and one of the main guys who play a role in these loops to add these corrections to the Higgs mass is the STOP, the supersymmetric top partner. And it turns out that the mass scale that you need to bring the Higgs mass up to 125 GeV is of the order, let's say, 1.5 TeV to 10ths of TeV. This plot is for tangent beta 20. If you have lower tangent beta, it can actually go higher. Now, one thing to remark here, this MS is actually the geometric mean of the two stop masses. So it's if both of them are at the same level, it's the stop mass. But if there is some splitting between them, one can be significantly lighter than the other one. So this scale needs to be seen in that with that remark. So it can be definitely lower than this. Now this range is possibly outside of the LHC range, so it's important to think of future colliders that could access this regime. However, the region up to 2 TeV order of magnitude might be reachable with the LHC, and we will discuss this in this talk. Now there is some tensions with naturalness, but often when you quantify naturalness, this has been done in a little bit too strict way, and I think how we probably discussed this in great detail. So things are not as bad as they might seem in more naive quantifications of naturalness. And of course, I only use the Higgs mass argument here to place SUSY in a certain mass scale. There's many more things you can do. You can include also constraints from many other areas. It can hints from many other areas like flavor or G-2. I think John will afterwards give a more complete overview of this. So now, where is SUSY hiding? Well, from a naive experimentalist view, there's two possibilities. I just put a random SUSY plot here from the LHC calibrations, as you've seen hundreds. So on the x-axis, typically the mass of the particle, this particle we're looking for, and the y-axis the LSP mass. And well, there's two places where SUSY can hide. Either it's a higher mass, in which case we just need more data, more statistics, higher luminosity, higher energy. So we need an upgrade of the accelerator. So on the first one we will have for sure already is the high luminosity LHC. Or it might be hiding in the cracks at low mass, but it's escaped our searches because the particles, resulting particles from decay are very soft or hiding in some way. This happens frequently in compressed spectrum areas. In which case, you could argue you need to upgrade the detectors. And this is a little bit simplistic. Clearly, there's a big interplay in between. For soft things, the thing you might want to do is to give them a good ISR boost. And to get an ISR boost, you pay a factor alpha S, order of alpha S. So you need basically more statistics to have a fraction of the events with a big ISR boost. And so again, we need more statistics. And clearly also the upgraded detectors are needed to be able to handle an upgraded accelerator, the conditions of high luminosity. So we'll try to discuss a little bit these two, number one and number two here. Looking at the experimental talks this week is really a beautiful program. You've heard many details about the SUSY searches at the LHC with wanderings into G-2 B physics, direct detection, dark matter searches, with dedicated technical talks on high luminosity detectors, physics perspective, statistics, machine learning. So one thing that I tried to add here in this talk, which hasn't been really focused on too much, is this upgraded accelerator. So just give you some information about what's been done and what's going to happen in the future. And then I'll come back to number two. So just a reminder, what we did during run 2 is of the LHC. You can see here the data collected during run 2. It was an important run because for the first time we were running at 6.5 TeV per beam, so 13 TeV center of mass. We went to 25 nanosecond bunch spacing before it was 50 nanoseconds. So operating with more than 2,500 bunches in the machine. We reached the design luminosity of 10 to the 34, which was already considered originally as very aggressive. And we even doubled it. So we went to 2 times 10 to the 34. And under these conditions, we delivered about 160 inverse femtobarn to ATLAS and CMS at a pileup at the end of around 35. And now, what is coming next? So in the past, since the end of run 2, so end of 2018, we've been upgrading mainly the injector chain in the past 3 years. Did a lot of maintenance, consolidation works, and then preparing for the high luminosity LHC upgrade. Also, ATLAS and CMS have done some minor upgrades to their detectors. ALICE and LHCb have actually done major upgrades. So for them, run 3 will be very important. And then, so the idea is now to run. I already said this schedule still has 3 years, but it will be 4 years in run 3. And then we will have another LS, which stands for long shutdown, where the HL-LHC installation will be finalized and there will be major upgrades of the experiments, ATLAS and CMS. And then we're going to go straight up to the basically another factor of 10 in luminosity, going to 3,000 or 4,000 inverse femtobarn. Now, what are we actually doing when we say upgrading the machine? Well, it's interesting to look at the formula for luminosity. So luminosity is given by this formula. So there's the intensity per bunch, meaning a number of protons in the bunches in the machine. So this is something you can try to push up as much as you can. Then there's the revolution frequency. You cannot change that. The number of bunches in the machine, you can also try to put as much as you can. Divided by 4 pi, and then it's a beam dimension, so the sigma of the beam in x and y in the transverse plane, so that you can try to squeeze those as small as possible. Now, so this sigma is given by the square root of the normalized emittance times the beta function. So you will see in the next tables, sometimes you will see emittance and a beta function. So emittance is constant over the machine, but then the beta, you can actually squeeze the beta to very small numbers at the IP, at the cost of a blow up a bit further. But what you really want is a small beta, therefore small size of the beam really when they collide. So those the numbers that with the circle around is things you can still play with a little bit for the upgrade of the machine. Now here's the parameters of the high Lumi machine compared to the nominal one. So as you see, one thing that we will do is to basically double the number of protons per bunch, and that's why the whole injector chain had to be upgraded. We can reduce the beta star, so basically the size of the beam at the interaction points. The goal is here to go all the way down to 15 centimeters. At the moment, we can go down to about 30, 25, 30. And with these numbers, putting that in the previous formula, that also a little bit improved other things, you get to the luminosity that I circle here. It's actually 17 10 to the 34. Remember, the original design was 1 10 to the 34. We can go to 17 to the 34. If you do that, you will get the right plot when it comes to pileup. So pileup meaning multiple collisions in the same bunch crossing. You will actually get 400 events colliding on top of each other. So basically, proton collisions will start to look like heavy ion collisions. Now, this is not something we're actually going to do. What we're going to do is we're going to level the luminosity. So this is something that you may not have heard too much about in the past, but this will be critical in the upcoming runs. So if you would just, you know, let the machine fill it with all the optimal parameters and then let it go, you get the red line here. So the luminosity will fall off as the beam will kind of burn up, in a sense. What you can do instead is to defocus the beam a little bit in the beginning so that the burn up is slower, and every time it burns up a little bit, you squeeze a bit more. So it's not an actual straight line, it's a little zigzag. So every time it falls off naturally, it falls off naturally, you push it back by just squeezing a bit more. And then you can have a longer lifetime of the beam, so it doesn't burn up that fast. And so in the end, the integral under the blue line is not that much worse than the integral under the red line. Plus, you can do this with a lot more friendly radiation environment and a lot more friendly pileup environment for the experiment. So that's the smart thing to do. So what we'll do is level at 5 times 10 to the 34, which corresponds at 140 pileup interactions. So this is something that the upgraded detectors will have to deal with, and we'll come back later to how we do this. Now in level mode, so the main thing that drives the leveling is the bunch intensity, number of protons per bunch. And as I already said, therefore you need the upgraded injectors, and this is exactly what's been happening in the past 3 years. So let's not forget the LHC injector complex in itself is one of the largest accelerator facilities in the world. So the SPS is a 7-kilometer accelerator after all. So the first thing that happened is LINAC 2. This is really the very beginning of the chain, which is the first linear acceleration of the protons, shut down in 2018 after 40 years of service, and a new LINAC was built in a new building. You might have seen that if you were on a certain site, which will inject at higher energy, 160 MeV now. And it will actually not even inject protons, it will check protons with 2 electrons attached to it. And there are advantages of doing it, so you can pack more particles in a bunch, and afterwards you can strip those electrons off. It's a trick to get around some limitations with a bunch charge. Now, construction of this new linear accelerator was completed in 2017. There has been extensive commissioning in the past years, and this year, in the beginning of this year, it's been for the first time active, and is performing actually very well, even better than foreseen. Also, the booster then, which is the accelerator that accepts the input from the LINAC, has to be adapted for the negatively charged hydrogen ions at 160 MeV, and it will strip off the electrons, and then the energy of the booster is actually upgraded from 1.4 to 2 GeV. So keep in mind, this is an accelerator from the 70s, and the magnets actually did not have to be replaced. The magnets could handle this new energy, but new power supplies and new RF systems were needed for this extra boost. And then also the PS was upgraded to accept the injection of 2 GeV beams. So the higher energy, if you go quickly to higher energy, you have more stable beams. So this is definitely an advantage to go as quickly as you can to high energy. And then also here you needed RF upgrades to be able to deal with this. Finally, the SPS, so the 7-kilometer accelerator, had a major RF system upgrade, new solid state power plants. In fact, this is the biggest solid state power plant in the world. That's now been installed to power this accelerator, and then a lot of measurements have been taken to make sure that the beams pass from one to the next accelerator without too much disturbance in their stability. And of course, if you have a more intense beam, more particles in the beam, you also have to upgrade your beam dump and all your protection systems. So all of that's been done. And actually, we've already run it this year, and the whole chain works beautifully. The LINACs, the booster, the PS works better than expected. The SPS had some struggles in the very beginning. There was some more downtime than foreseen, but by the end of the year, so by now basically, most of the commissioning has been done, and we expect next year a very good availability of the whole injector complex. Things that will still come in the future is a complete redesign of the regions, the accelerator regions around ATLAS and CMS, in order to achieve smaller beam size, so really squeeze the beam more and be able to withstand the radiation from these increased luminosity. So it's a lot of the work is not only to make sure we can create the luminosity, but also to be able to handle it, not break the machine while doing that. So for example, all the electronics that are now in the tunnel need to go in a parallel gallery away from the machine, because there will be too much radiation. Now, with this upgrade, once this is all done, we expect to be able to get 250 femtobars per year to ATLAS and CMS, which allows us to reach 3,000 inverse femtobar by 2037. That's 20 times more than what we have at the moment. And there are some margins in the design. So if we go a little bit higher than foreseen, up to 7.5, 10 to the 34, we could even get to 4,000 by, let's say, 2040. at the price of a pileup of about 200 events per crossing. So this is the schedule in these two cases. So see that this is still, I mean, all these schedules have to be moved up by a year after 2020. Basically, everything has been shifted by a year. It's after COVID. It's not only to do with COVID, but a large part of it is. And so, as you can see, then depending on how aggressive you want to run the machine, you can get to 3,000 or 4,000 inverse from to burn. So we have definitely a good physics program till let's say 2040. And after that, we need to make sure already now that we have a new accelerator to take over. Now, to be able to handle all of this, you had a dedicated talk by Frank earlier today on the CMS upgrade, so I'm not going to go in major details. But of course, the main thing is that they have to be able to withstand the radiation environment. That's the first thing of these upgrades. Then, for example, in CMS, the end cap crystals, they will be completely black. So these are fully transparent crystals right now. They will be completely black by the end of run 3 already. So they will be replaced with a new detector. And then if you can build a new detector, you might as well try something new. CMS is trying a full silicon, partially silicon, 600 square meter silicon, a highly granular calorimeter that is not so much optimized. You know, the crystals was really Higgs to gamma gamma was the main thing in everybody's mind. Now it's more boosted topologies, be able to figure out everything in boosted jets. So their advantage, you have big advantages with high granularity calorimeter. Tracker gets extended to high granularity, less material, and also the timing detector gets added. So the advantage of using timing, first of all, it was not possible earlier because the resolutions, the timing resolutions you needed are only achievable since quite recently, the past couple of years. And the idea of that is to really be able to say if a proton collision came from the beginning of the luminous, so in the middle of the luminous region, or somewhere at the edge. So the pileup at the edge of the luminous region, you can basically remove from the one in the middle by just using this time. Same for ATLAS, also upgrades to be able to also take more data. The DAQ has been upgraded, triggers have been upgraded, smart things are happening. For example, triggering on trackers, on tracks only, which is not possible currently. Then even try to, at the first level of the trigger, to add, do some kind of particle flow, add tracks to muons, to calorimeter information, and really try to keep the thresholds similar to what we've had before, but at these much higher intensities. Also, ATLAS is doing a timing and extended muon systems. Now, what do we know about the performance of these detectors? Well, as I just argued that timing is something that can really play an interesting role. For example, on the left plot here, you see this is isolation efficiency of a lepton, electron or muon. You see that adding timing, you get these colored plot dots. Things are a lot more stable at high pileup than if you do not use this time information. For the second plot here is the jet mass after pileup subtraction. So you can see that with these new detectors, things are rather stable at very high pileup. B tagging and the third plot. So you should look at the yellow line is pileup of 200, red line is pileup from 140, and we're still talking about 80% B-jet efficiency for a mistagging rate of less than 1%, which is actually amazing. Is better than what we were doing at zero pileup at the beginning during run 1. And then of course the first thing is that you have a high efficiency to detect everything in this difficult environment. Now, okay, so with this upgraded accelerator and these upgraded detectors, what type of physics can we do? Well, you had a dedicated talk on the reach at High Lumi by Cezanne earlier today. So, for example, for gluinos, seems that the High Lumi LHC can reach about 2.5 TeV. The stop masses, so you have the right plot here, it seems to indicate something around 1.7 TeV. Now, my gut feeling here is that improvements are possible. And the reason why I'm saying this is that I have not been involved in this analysis, but I was involved in the FCC HH stop analysis, and we had exactly the same problem that at some point at high mass, our boosted topology, the way we did we handled boosted topologies at the LHC currently was just by far not good enough. Things were a lot more boosted than what we are used to, and we had to completely redesign a new tagger for these topologies. And so originally, by using the standard boosting topology identifiers, we could reach this FCCHH. We could reach 6 TeV. After an optimization, we went to 11 TeV. So really a major improvement. So I have the feeling that also here, maybe not as much, but some improvements can be done. You see also a very unnatural kick here. So I would hope that we can go closer to the 2 TeV region by improving tools and improving analysis. So even at 2 TeV, you still have a decent amount of, if you look at just a cross section of production, is still reasonably okay. So I think we will be able to get closer. Electroweak particles, these are the projections. So for example, Chargino projection, where both of them decay W-like, you reach 800-900 GeV in mass, Staus around 700 GeV. Pure Higgsino scenarios, which are actually, quite favored in many scenarios. There, the reach is still pretty low. You see 300 GeV. With lots of holes still in between. Now, I think the holes can probably be recovered by being smart, but going much above 300 GeV, I do not really see possible. So I think, yeah, for Higgsino will always be a weak point of the LHC. RPV SUSY. So yes, so RPV, there's really many decays to look at. Very few people have had the courage to dig through all of it. Herbie Droyner is one of them, and he's published some reviews. I think the problem is that most signatures are actually covered. There are few are missing, in particular with tau final states, but they're scattered over many different physics groups, not only the SUSY groups, but also Exotica, beyond second generation, many different groups. So I think one thing that we should try to do in the coming year, I think both ATLAS and CMS SUSY groups have agreed to this, is to try to improve our understanding of what we've done, our presentation of all the RPV searches that are being done, and really identifying what is actually missing, trying to cover that. So this is something that hopefully will happen. Now, a comment about the search strategies. So it is actually interesting to compare the strategies at the beginning of run 1 with those at the end of run 2. So we've evolved from simple cut-based approaches to multi-category approaches involving BDTs and machine learning techniques, and sometimes it got quite complicated. Now these approaches are more powerful, of course, but there is also a loss of transparency. And in fact, ATLAS has been pushing back a little bit against this. They have sometimes on purpose kept things more simple than they could have to keep that sense of transparency. CMS has sometimes included a simplified version of a search, so it would be easier to reinterpret afterwards. So that would be in the appendix of the paper. There would be something that got close to the performance, not quite the same, but with a much simpler way. Now, I think these trends will continue. You cannot really stop this, but we should keep in mind to optimize to really, the idea is to discover something, to be ready to argue that you have really seen something in a robust way. And optimizing for exclusions in simplified models is not really the most important thing there is. So I'm a little bit skeptical about using too fancy of these techniques in the analysis part itself. On the other hand, for object reconstruction, for example, B tagging or anything else that has to do with physics object, that you can really control the performance of these algorithms in a data-driven way. For B tagging, for example, you can take a TT bar sample and really measure how well you do the B tagging, or a QCD sample, or you measure the mistagging rate. So no matter how complicated your approach is, you can really do your efficiency versus mistagging rates in a data-driven way. There is absolutely no problem, and you can complicate your things as much as you want, and if you improve that's just great. So there is really no showstopper there. For analysis, I would advocate keeping things still a little bit transparent, because in the end, if you do see an excess, you have to be able to convince people that there's really something there and that you're not fooling yourself. Yes, then another remark that I'd like to make on the future is that the days of fast luminosity doubling are over. So excesses, we used to, every 2 months we would have double the luminosity. We would, 2015 we had 3 inverse femtobar. In 2016 we had 30. 2018 we had 160. So those days are over. Things will build up much more slowly. We'll have to be patient. And I think one of the things we need to really make sure we can do is to so basically going from nothing to 5 sigma will take a really, really long time. And I think it's very important to also try to look at many different channels for the same thing. For example, in the stop here, it's important to look at the fully hadronic final state, single lepton final state, dilepton final state. And if you look at multiple channels at the same time, you have definitely the advantage that you can have 2 independent cross checks. You have an excess is real, and you start to see excess growing in 2 channels that like this. That's a very powerful hint. You can combine them to get a higher significance, and so we really need to make sure that all of these channels are covered. This is not so easy as you think. Often people are, for example, in the case of the stop, the dilepton, you see alone it's less powerful to exclude, to put limits, and we actually had to convince people to really work on this, and they were a little bit discouraged given their projected sensitivity. So I remember at one point I had to invent a model where the stop would decay to B chargino and then the chargino through a lepton, so there was 100% lepton, so they would be really the best to motivate them. But even without that, it should be clear that it's not because a channel does not put the best limits that it's not absolutely essential to have it. Then something outlook to the near future for the Run 3 plan. So we just come out of a week of workshop with the operators of the accelerator. Run 3 will start in the last week of March. So the day before yesterday, the date was the 31st of March. I think today it's moving forward by a week. So I guess around the 25th of March. The energy will be, it will not be the fully 7 TeV per beam, because the risk of doing some damage while quenching the magnets to train them all the way up to the 7 TeV is considered too high. So not that you would particularly damage the machine, but you might create a delay. You have to go in to fix something, but every time you have to go in to fix something, even if the fix only takes a couple of days, you have to warm up that sector, do the fix and cool it down, and the warm up and cooling down takes 3 months. So we do not want to risk having another of these warm up, cool down cycles that would push the whole schedule behind by 3 months. And that by that you would lose a lot more than what you would gain from going from 13.6 TeV to 14 TeV. So it's not worth the 0.2 TeV is not worth the risk. Though I have to say that half of the accelerator has been trained to 7 TeV per. As I said, the current schedule for the 3-year run is very, very likely to become a 4-year run. And then the official target for run 3 is 160 inverse femtobarn for ATLAS and CMS, so to double what we had in run 2. However, that's conservative. So hopefully, with some realistic estimates, we will get the first year about 30 inverse femtobarn and then 80 inverse femtobarn per year. So about 270 at the end of run 3 with a pileup of 53. So hopefully, we will do more than double and close to triple the luminosity of run 2. Summary, so LHC will deliver 20 times more luminosity than it has up to now. Keep in mind that the days of fast luminosity doubling are over, and we need to keep focused and try to correlate excesses. The experiments have designed a major upgrade program that allows the full exploitation of the high luminosity. SUSY is not that, and it could have very easily been that, but it is not. And it's still the best BSM theory out there. I have not heard of anything better. The fruit is not hanging low though, but so it means we will have to climb into the tree and think of smart ways to build ladders. So that's the challenge now for us. Keep in mind it's a marathon, not a sprint. It will take new ideas. It will take hard work, but SUSY is definitely worth it. Thank you.
Thank you very much, Filip. I particularly appreciated your statement that try to prepare for discovery and not exclusions.
Yes.
I think this is something we really need to keep in mind, and more so with the high luminosity. So I really like very much that statement. Let me see if I have any raised hands and Q&A because of this. One moment.
You might have lost some.
Yeah, I don't have anything in the chat, and Q&A I might have lost. But in chat right now, I don't have anything. I don't see, yeah, I see Pietro raising a hand. So Pietro, can you please ask your question?
Yes, I
just comment, whatever it is.
Hi, Filip.
Hi, Pietro.
I wanted just to make a couple of remarks. Yeah, this statement, SUSY would be dead if Higgs mass had been higher than 135 is far too strong.
Yes, I agree.
Simple
course, I mean, I know because I was involved in this 135 many years ago. So, okay, this of course is a bound that you get in the MSSM with some assumption on the value of the stop masses. So you could, in principle, have a heavier, I mean, accept very heavy stops, and you could go above that, or you could consider an extension of the MSSM where you have additional contribution, like just the NMSSM, and you can again go above that.
Yeah, Pietro, the argument would not really change if I would write 160 instead of 135.
Okay, then you would need more
window of 50 GeV instead of 20 GeV. While we were looking up to 1 TeV. If you don't take SUSY into account, the window is really 1 TeV. So if it's 50 or 20, I think is not correct.
Yeah, no, I understand, but then this really catches the eye, and then this comment comes naturally. And then I wanted to point out a second thing in your subsequent slide. You are very correct in saying that when we say these plots show that the stops have to be above the TV scale. It's under the assumption that the masses are more or less comparable. Then studies have been done also in theories where like you have a split spectrum and you can have a lighter stop. The only remark I would make is that this, when you say it's the geometrical average, that's strictly true for the logarithmic term, but I think this xt term that gives you the further enhancement, it's probably gets a bit suppressed if you have a split spectrum. So you probably need to go quite a bit higher in the heavy stop than you would expect from the naive formula. But of course, I mean, then you would have to just build a different calculation for the Higgs mass.
Okay, point taken.
Okay, so right now I don't see anybody's hand, so I take the chair's privilege and I ask a question. So
there is one. There, Rohini, there is a hand by Howard.
I didn't see that. At least my screen doesn't show it. Okay, Harvey, please go ahead. Now there are more. Yeah. So Harvey, please go ahead.
Thank you, Filip, for a very nice talk. Could you give a quick update on what the status is on CERN beyond High Lumi LHC? What's the next thing, big thing?
So yeah, right. So the main focus is of CERN is FCC. As you know, we came out of the European strategy without a very clear decision, and this is a little bit unfortunate because a more clear decision would be able to focus more. So now things are still not, spread around over many options, and then you do not drive, the best, well, the number one option as strongly forward as you could have if you would have eliminated some choices. But it was just not. There was no convergence in the European strategy. So that means that there's still a lot of work on many options, including muon collider. Not from the experimental physicists, but from the machine people. There is work on the muon collider. The main work is on FCC. Not so much the HH, that's kind of slowed down a little bit, but on EE, because that will be the first machine to happen. While other options, such as click, is still being kept open on on a small level. So as you heard a little bit in what I was saying, my worry is that if you do not make a clear choice soon, and you spread your manpower over many options, you're slowing the whole thing down. I would have preferred to make some hard choices now, and then really go forward with that choice, no matter what it would be. Voilà, that's the situation at CERN.
Okay, so Arnav had a next question.
Yeah,
sorry.
Remark that this European strategy discussion is now happening in America, as you know very well, and I would encourage everybody to participate and bring their input. And it would be nice if out of the SNOMAS effort in the US, there would be a more focused view of the future.
But Filip, may I just ask one more question in this, then you continuing, since you brought in also SNOMAS now. So I have forgotten, but when is the next review in the European strategy? Because there was supposed to be a 26. Quickish review again, right? I mean, when was that supposed to be?
The what review?
For the strategy, there was some sort of a quicker, earlier review than the usual 5-year gap, right? I mean, somehow I had this memory. Some discussions will happen. So
I'm not aware about the interim. I don't know. The next one is in 26. But
20?
26. But there might be an intermediate point that I'm not aware of.
Okay. Then obviously I have got wrong information. So okay.
No, I might not be aware of it. It's as I said, my feeling is it would be better to pick something, no matter, they're all good options in a sense.
Yeah.
And focus on that rather than keep all options open and not move fast enough, because
yeah, I think I agree with you.
It would be really great if by the time we finish with the High Lumi by 2040, we could, almost immediately after that roll into
make
the
a smooth transition.
not have a huge gap.
Yeah.
And that means there's only 20 years from now. So that means, from working everything out in detail, from finding the people to do it, finding the money, focusing, 20 years is not that much.
I think the E plus E minus machines have suffered from this in some sense. And what you're saying makes perfect sense. But maybe there is another hand up that was by Arnab. So that may be away from policy. So Arnab, what's your question, please?
I was just having a question regarding the LHC parameters that you have shown. I mean, can you go back to that slide?
Yes, the
high luminosity.
Yep.
Yes.
This one.
So my first question would be: I see that there is the number of bunches in the ring is going to be decreased a bit I'm talking about the small n. So is it because we are increasing the luminosity, or is it related to that, or for some other reason?
These are small technical reasons. So you see that the first three columns. So typically what we run with is this BCMS, that's kind of most optimal, this BCMS scheme. So there are just some technical reasons why there, you cannot fill the full 2,800 bunches. There need to be some gaps for technical reasons. I wouldn't search big mysteries behind that. Now the last column is something we'll only use, this 8B4E. It's with extra, let's say, little breaks and this is this is a special scheme for lower heat load, because one of the critical items is the heat load that you give to the triplets. The triplets are the magnets who do the final squeeze before the collisions happen, and they get a lot of radiation, a lot of heat load, and they might break. So if the heat load that they will get is too high, we may go to this scheme with less heat. But if the heat load is acceptable, we will just go with the 2,700 something bunches.
Okay, I understand. Thank you.
Okay. So I think we are really running quite late. So once again, let me thank Filip for really a wonderful talk.